Hey everybody, this is the chapter 15 lecture from our book. We're going to get more into regression this time, and with it, we have a couple of learning objectives we have to cover. We're going to look at tests for individual significance to look at individual variables. We're also going to be looking at the test of joint significance. Can we see multiple variables, independent variables, x's taken simultaneously, and what do they look like? And then testing them in batches if there's any restrictions to be put on. Essentially, can we hold some out and still get the same result? Then something a little different than the confidence intervals you've seen before. Let's look at confidence and prediction intervals based on the y value, the prediction we actually make. Can we set up a confidence interval for them? And then look at some of the assumptions that we have to make going forward with our ordinary least squares type of regression and some assumptions that are out there. So to start, this is from your book, in case you're wondering, or if you're from a different book, just gives you an opportunity to get an example. Imagine a scenario where we're trying to predict winning in baseball and the percentage of winning based on the batting average of the team and the ERA of the team. And we often wonder which one's more important, your batting average or your earned run average. So we want to run a test to see, is it batting average versus win, ERA, earned run average versus win, this win, or maybe both taken simultaneously. So we'll do all three. So we'll have three different models. And notice they're models because we have an error term in each. Error, error, and error. The leading coefficient, beta here, beta here. We have our intercept term. We have beta 1s for batting average for error. And now we have this new beta 2, which is the second variable. We want to run all three. So what we'll do is we'll say, let's run all three. We could do this easily in regression with Excel. We get their multiple r, their r squared adjusted, which adjusts based on the number of variables you add. We penalize essentially by adding additional independent variables. We'll calculate the standard error on each, which allows us to see really starting towards how much noise is there, and then we'll look at count. So it's the same data set. From this, we see that if we looked at adjusted r squared, which is the only one that allows for multiple here, we see that it has 69.45% of all the variation that's happening in the model can be explained by batting average and ERA. Here it's about 45%, and here it's about 20%. So clearly Model 3 is explaining more. From this, we can say, okay, now, fitting the entire model, what if we tested all the betas, beta 1, 2, all the way to k? You can test to see whether or not you need them. Do you set it equal to 0 or what you believe it should be or not? Is it an upper tail test? Notice the beak here is pointing to the right, so it's an upper tail, left or lower tail to the left. The t-statistic we use is a little bit different than we've seen, even though we're looking at b versus beta. Where it comes in a difference would be here the degrees of freedom. Now this comes from the ANOVA. We know that there's going to be a particular number here, the number of variables we have. Let's just call it k. If we take k and add it to n minus k minus 1 plus k, we get n minus 1, which is your traditional t-statistic, degrees of freedom. For this statistic, though, we're going to test each beta. So here's our model. Notice again, it's a model because it has error. When we estimate it, that error will go away. These will become b's, and this will get a little hat over it. So the coefficient, as we look at it now, we'll say is equal to 0. And we're going to say, is beta equal to 0 for all of these? And what we'll do is, using Excel, and Excel is pretty good for basic regression here. If you want some more advanced things, you can try JUMP or SAS or something like that, Minitab. But we want to test this 0 stance with a p-value. So what we're going to do is use this p-value from the all of Excel, and we're going to say, can we set beta sub 1 to 0 or not? So it's a two-tailed test. Beta sub 1, if we call it batting average, we look here and we see that its p-value is 0. That's less than any alpha. So if we say 5%, we would reject the null and say that beta sub 1 has to be something other than 0. So it's significant and needs to be included. You could also say the same thing for ERA. Both are significant on their own in the model. So we reject the null. When we look through this as a confidence interval, now Excel gives us all of these values. What we'd like to be able to do is find the confidence interval for batting average and ERA, and they're given to us. We can calculate them, sure. We take what we believe it to be, in this case, the B value, realized value, plus and minus the statistics and the standard error. But we'll notice here that 0 is not included here and 0 is not in this interval. The intercept interval really means nothing. It just is kind of a balancing item and allows us a fixed point to make sure that everything works out. Since 0 is not in either batting average or ERA's confidence interval, that means we can't set it to 0. That means they're both significant. What about joint? Well, that's when we take them all at once. We say, can we set all of the non-intercept betas, that's B1 to BK to 0, and get away with it? If that's the case, you don't even need the data. Your model is not significant. But if you can reject this, you say that you need at least one of those betas, at least one of those independent variables to exist. Therefore, in totality, they're significant. You might have 25 variables that are trying to predict something. Only one of them has to be significant for the model to turn to be a significant predictor. We're going to fall back on this F test that we saw in ANOVA here. Before we saw it as treatments and error, now we're seeing it as our regression. Here's that K, the number of independent variables. Here's that N minus K minus 1. This MSE, that's your white noise. This sums the squares due to error. You take the ratio of regression to error, and that gives you an F statistic. If that statistic converts into a p-value, we want that to be really low. That's your model significance. The F statistic with its p-value is model, T statistic with its p-value, those are variable level. So what we want to be able to do is create p-value. Now it's really hard to do this by hand. I'm glad Excel can do it for us, but it is kind of complicated. You have to calculate this and then do the F-dist in Excel. So we'll do it. Can we set both of them to 0 or not? Well, we already saw we can't. But we do know that when we create this F statistic, we get a value. So in the end, we're going to get an F statistic for model 3 here, where we had a value, and see that its F statistic, 33, turns into a p-value of 0. So it has no stance. If I go back a few slides here, you'll see that both this and this were significant, so therefore, by association, the model is significant in most cases. So we know that jointly they're significant. So 1, batting average, 2, ERA, are both significant, and together they're significant. And they do explain quite a bit of the model. They explain nearly 70%. What we'd like to do then is take it a step further and see if we can do any kind of linear restriction to our model. That means, can I look at a grouping of independent variables, x1, x2, x3, and take 1, for example, x1, and see whether or not you can exclude 2 and 3 and find that 1 is not significantly different than if you had all 3 in. That's a test of linear restrictions, and we're going to do an F test, except we're going to do it as a partial. We're going to compare what we restricted it to be, just one variable, or 2, or whatever you want to restrict it to, versus the unrestricted, which is the all-in, everybody's into play. And we'll create a ratio to F statistic just like we saw before. The restricted model, we have to restrict so that we can compare. The unrestricted says everybody in, and we'll go with that. So we'll create 2 white noise error terms, SSE for the restricted, SSU for the unrestricted. We'll take their difference and divide by a degree of freedom. Before, with the F test, we would see this as K, the number of independent variables. Notice this would have them all, and this would only have partial. This one here, however, SSU, which is everybody in it, would have N minus K minus 1. We saw that before. Now we're going to test. What we want to do is test. If we reject the null and say, you know what, we don't need them all, then restrictions aren't valid. What we're going to do then is take this case. Can we predict sales based of a newspaper? In this manager of a car wash in Missouri wants to determine whether or not their promotions improve sales. And is it by discounting their price? Is it by advertising on the radio or advertising in the newspaper? All 3, whatever, let's restrict. So they're going to say, can I hold out radio and newspaper and essentially get the same result in prediction if I just do sales versus discount? So I'm going to take all 3 versus sales and just discount versus sales. And if I can't prove that there's significantly different, they're the same. So if I really want to prove that radio and newspaper are important, I'm probably going to want to reject the null. So in this case, we set them to 0, 2, and 3. Conduct the test, short the restricted, 1, 2, 3. And notice they're still models, they've got error in them. So the restricted model with only 1 in it has an SSC of this. So it's got quite a bit of noise. The unrestricted has quite a bit less noise in it. So what I'll do is then take the sums of squares error with unrestricted from the restricted and see what happens. Take the difference. We say that the degrees of freedom is equal to 2 as we're doing a comparison. Then we have 36. That's in totality. So the 2 here are the 2 that we've pulled out and restricted. 36 in totality, n minus k minus 1. We had 40 observations to look at, 3 independent variables. Subtract 1 as we have to always hold 1 out. And we get an F test, and the F test says, we can reject the null. And when we reject the null, we say that, hey, based on the criteria here, can I set them to 0? If I set that to both to 0 and I reject it, I'm going to say, hey, at least one of them isn't 0 and is necessary. So in rejecting the null, I've just proved that at least one radio or newspaper is significant. Another example would be, hey, same scenario. What if I didn't know the difference between 2 and 3? So if I rejected and said, at least one of them is, now let's take a look. What if we thought they were the same? What if their returns are actually equal? 2 is the same as 3, or else they're different. What I'd like to do is set 2 as 2. And that is, here's the unrestricted model. Remember, we restricted it before. Now what I'd like to do is say, if 2 and 3 aren't different, here's 2 and 2 again. And I hold them out. Now I'll be additive. I'll add together radio and newspaper as a variable and rerun the regression. So I have that one here, this restricted. The unrestricted is put them all in. This is the additive piece. I go through this. And in the end, we can't reject the null. It's interesting. We can't reject the null. That means that they're equivalent. By not rejecting the null, we find that, we can't conclude a difference exists between the two, so they're essentially the same. With that, we're able to get a better understanding of the importance of variables. The next thing would be to look at, for this chapter, looking at these interval estimates. So we've just looked at whether or not the prediction is significant as a model. Can we restrict? Does it even matter if you restrict versus having them all in? That means, can you simplify the size? We looked at whether or not things are equivalent. Now let's look at the output by itself, the y value. The y value has a confidence interval. Until this point, you've only really done confidence intervals for univariate statistics. We're trying to pull something out mainly on the independent side and see whether or not I could create a measure of confidence around it. Now what I'd like to know is there a confidence interval for the dependent variable y? Now if I go back to this model where we try to figure out whether or not earn run average and batting average have an effect on the overall win percentage, we created a model. And what happens if we say, the ERA of a particular team is 4 and the team bats .250? What's the win percentage? Well, we just plugged and chugged and put them in here and we got .47. Hey, that's great. But you and I both know that's not going to be the exact number. So what we'd like to be able to do is determine really what's the confidence interval about that number. So we get a sense of, give or take, this is where it should fall, knowing that 47% should be somewhere in the middle. So we can do that. We can create a confidence interval for what we expect. That's kind of an on average value. But the one that's interesting and wider as an interval is something called a prediction interval, and that does it on an individual value. This instant, that value, what is it going to be? Now, it's hard to do this in Excel at first because it doesn't give it to you. Most stat packages give it to you, but we can calculate it for ourselves quite quickly. We want to look at the confidence interval and then the prediction interval. And with the confidence interval, as we know, here's what we would have a point estimate. Notice it's not a model anymore because we've done an expected value. This is what we generally see for a confidence interval. You take an estimate, you take a statistic, and you move it around based on the standard error. That would be your variance or standard deviation over the square root of a sample size. Well, what we'd like to do then is adjust based on what we want. So we knew that it was a team that had a 4 ERA and a 250 batting average. Let's subtract out that amount from what we know. So we do that. Here were all the teams with their batting average. Here's their teams with their ERAs. Let's subtract out the 25% batting average, so you bat in 250, then subtract out the ERA, and you get a new value, an X sub 1 star and an X sub 2 star. Let's see if we can predict this, which is the win percentage, based on these two new variables. Here we do it. We get a coefficient for the leading coefficient for X1 and X2, and we get their confidence intervals. But here's the thing. I'm going to flip down here one. This is what we saw before. When we ran this, we saw that it was 32, 754, 1153. Well, guess what we just got? When we see this, we got 32, 754, and 1153. They're the same. What's going to change, though, is the intercept. The intercept is now going to have a confidence interval. This is the number that we're interested in because we've adjusted. Remember, we said it was about 47% winning percentage with that group. Now I'm able to actually capture this in Excel as this is the range that we're expecting to see for a team that bats 250. It has an ERA of 4. So between 46.73 and 50.21. Here we go. This allows me to see for that estimate, what do we expect a team to bat? So it's kind of difficult, and it's a different level of statistics. What we're trying to do is actually adjust based on those numbers. The prediction interval takes it a little bit farther. It's going to incorporate a particular value here of the standard error. So in a regression, you're always given where your R squared adjusted, and your standard error is always at the top before you get to the ANOVA. Essentially, it's the same thing as we just saw, but now I'm incorporating in an additive piece. You just throw in the error. That expands the interval, and this is going to be what happens on a particular instance. It's a little difficult to understand, I know, but confidence interval looks at things on average. Prediction interval looks at it for a specific instance. Easy for me to say. So this is off by, should be a 0 in here, but we take that 2.5, that 4.0. We know what we had before, 48.47. That's the prediction that we had when we plugged in the numbers. Now what I'd like to do is float this. Here is the standard error. Here is the value that we calculate. I'm sorry, this is the standard error. This is the error term that we actually added in. And we can create this instance. There's a good example in the book on how to do this if you're using the Jaji and Kelly book. This interval, quite a bit larger, 40 to 56 versus 46 to 52, the larger is a measure of not confidence, but prediction. This is an instance. So this is one team, one time, versus on average on all teams if you looked at them on a long-running value basis. So when I revisit this, I can see where that number come from. Well, we're able to see from all of what we've seen before the ability to visit Model 1, Model 2, Model 3. Standard error was delivered to us 0.0375. That's where it came from for this. Real quick, a lot of validation has to happen in regression. There's a lot of assumptions and things we do wrong. Couple just quickly, and these are always explained very well in every stat book, but here's what we have to understand. One, the model itself, notice the model has the error term. It's linear in the parameters. So what we're trying to do is establish a linearity agreement between betas and the model. Can we take them one at a time? We want to make sure that that's the case, and it's pretty simple to do as we look to the model. Next, we want to make sure that when we have the model itself taken as expected value and make it, what do I expect y to be? I eliminate the error. It's just a simple condition. The one that I want you to focus on is this idea of multicollinearity. Taking your independent variables. Are any of the independent variables taken together, two at a time, highly correlated? So x1 and x2. If those two have a high degree of correlation, say an R of 0.8 or higher, or an a negative -0.8 or lower, they're highly correlated. Essentially, they're telling the same story. So we want to make sure that we can eliminate them if at all possible. There's a lot of other things, and you'll see them pop up. This idea of homoscedasticity, looking at the error terms, it should be very constant, not voluming in and out like a trumpet. Looking for correlations. We want to make sure the error terms are uncorrelated. If they become correlated, it becomes an issue, especially as we look at time series and on and on. Error terms are going to be normal. We can test that. But the reality is, when it comes down to it, for what we're trying to accomplish, multicollinearity is the most important thing. X's by themselves, taken together, two at a time, are they correlated? So that's a good overview of what we're doing in Chapter 15. We should move then, after this, from general assumptions into larger pictures of regression.